잠시만요. 이거를 좀 시스템이 좀 이상한 것 같습니다. 혹시 이 지금 제가 말하고 있는 게 보이는지를 유튜브 채널로 좀 확인해 주실 수 있으세요? 오프라인 상태라고 나와가지고 여러분 중에서 인터넷이 되시는 분들이 채널에 가서 지금 이게 나오고 있는지를 좀 확인해 주시면 좋겠습니다.
지금 나옵니다.
아, 그렇군요. 그런 것까지 다 들렸어요. 네. Okay, so thank you for checking. The live streaming is working properly. Okay, welcome to lecture number 4. Still, we are in the discussion of diffusion. So, do you remember previous lecture content? So, in the previous lecture, we have introduced the diffusion equation in the microscopic or macroscopic point of view. And at the time, we thought about the steady state condition. So since steady state condition assume that all kinds of time derivative goes to 0, so we had only now second derivative of our dopant concentration over the real space. That was the equation we have solved. So maybe you remember that previously we have assumed certain boundary values at x equal to 0 and another value at x equal to L, and the analytic solution was just a straight line between connecting these 2 points. And I ask you to solve this system with our numerical solver. So maybe you remember I ask you, so number of 6, so 6 points were introduced, and I explicitly showed how you can construct a system of AX equal to B. This B contains some boundary conditions, and A contains also boundary condition and our diffusion equation. So what was your opinion about homework number 3? So have you already done these homework problems without any difficulty? So if you have any question on our previous homework, then please feel free to ask me. So if you don't have any questions, but right now you feel that I have no question, but you know, whenever you have any question, then please interrupt me. So to me, it is more important to ask your question than explain already recorded contents. So you know, this course has been taught many times, so you can find many available recorded videos. So your question is more important. So let's just continue our discussion on the diffusion simulation. So previously you remember that we had introduced this diffusion equation, and in the last lecture we assume okay, steady state, so this one goes to 0. After that we have just a second order differentiation, but now we wanted to keep this time derivative term. Then what happens? Now we have to solve our concentration as a function of real space at the same time the time variable. So we have to consider this solution. Although you know this is 1D quantity and also this is 1D quantity, so at most it is just a two-dimensional problem. However, I wanted to tell you that there is some difference between this real space and time domain. So usually these time domain variables are interacting so closely. I mean that here you have many points, mesh points, and information stored at this point. For example, certain concentration at certain position xi is quite much related with the information at the neighboring point here and another neighboring point shown here. They are closely related. Of course, long time. Let's say that this is a time domain, and now we have C, the same points. However, now we have a different time index, k plus 1, and happen to be, let's say this is the time domain. So let me just wait for a while. Okay. I'm afraid that today our system is not working properly, so please wait for me a moment more. Okay, so then we have t sub k time points. So here I introduce certain axis along position and another axis along the time variable. So in this case, of course, we have the communication between one central point and neighboring point, and central point at present value and with different time indexes. So t sub k plus 1 and t sub k of course are closely related, but usually when we solve this kind of problem, our assumption is that okay, we will just solve these quantities as a whole. So this is one set of unknown variables, and also we can find different set. So say this one, this one, this one, or other values at time index of t sub k plus 1. In this case, we will treat these quantities as another set of unknown variables. So we will also try to calculate this set. So are you with me? If we are having different point of view, then maybe we can try this way. For example, here. So here we have different positions and different times, and we can treat it as just a two-dimensional space and discretize our equation both in real space and time domain and solve this global set. Then we will get the solution immediately with this large system. But instead of that, usually we do this time-wise or calculate the solutions at a given time instance. So once we calculated this time, then we calculate at this time and next time and next time. It's not like this real space. In the case of real space, we treat them as a one system. So please note that the difference between the real space and time domain in our calculation. So typically time variable is called as margin, time margin. So one time, another time, next time, second next time. This kind of time marching technique is understood in this course. So are you with me? So now if we adopt this kind of time marching approach, then what we have to do is try to solve the system at a given time. When the solution at the given time is obtained, then we can march the time, then calculate another solution at different time instance. So that is the way we do. So fortunately, here we have second derivative with respect to x and first order derivative with respect to time. This second derivative was discussed in our previous lecture, and do you remember its form? So under the uniform grid whose spacing is just delta x. So now I wanted to say that xi is given by I multiplied delta x. If we have this uniform spacing, then we will have this discretized form of our second order derivative. So how did we get this form? So first of all, we calculate first derivative terms. So I mean that here we have xi, and here we have xi plus 1 and another xi minus 1. They are all uniformly spaced. Then we calculate the first order derivative defined at this cross point and this cross point. So that was approximated as delta x, and here we have some quantity at xi plus 1 minus xi. So that was the quantity defined at this point, and here we have the same point or similar quantities between xi minus and xi and xi minus 1. So by taking the difference between, once again, these first order derivatives, so this one and that one, eventually we get an approximate form for our second order derivative centered at x sub I. So please note that when we try to calculate this second order derivative, then now we have the information about the value at the center point and value at two neighboring points. Okay, so of course, when these c values are the same, for example, c at xi equal to c at xi plus 1 and c xi minus 1, then what will happen? If we have this kind of uniform or constant c values, then immediately this guy, and this guy, they are counterbalanced, and we will have immediately the vanishing second order derivative. It is quite obvious because when we have a constant, then taking its second order derivative, it should vanish, and it is satisfied in this approximated form. Okay, so anyway, it was covered in the previous lecture. So now our remaining task is just to discretize this time derivative one. So today we will talk about how can you treat these time derivative terms in our diffusion equation. Okay, so are you with me? Do you have any question on the quick review on the discretization of a second derivative term? If you don't have any question, then let me just move on to the next slide. Of course, when you consider this discretization of a time variable, there can be so many different ways to consider this time derivative. However, I wanted to just introduce the simplest one. So this so-called Euler scheme is the simplest one we use in the TCAD simulation. So of course, in your commercial softwares, more advanced ways to calculate this time derivative term is provided. So however, we will just restrict ourselves to the simplest one. Okay, so why? Because it is simple, and there we can find two categories, so two schemes, and understanding the difference between them is important in my opinion. So one is forward Euler scheme, and one is backward Euler scheme. In the fourth one, let's think about this time derivative. Okay, every time we are now talking about the central point, because this is partial derivative with respect to time, so position is just fixed at x sub I. So although I write down c of t sub k plus 1, it actually means the quantities like its position is always x sub I and time index is this way. Okay, so I will with me, although I sometimes write down like c of x sub I and c of t sub something, but in general you have to consider two input arguments to calculate this C value, and when one is obvious, then that is understood in this notation. So please don't be confused with this shorthanded form. And the difference is like this. Please have a look at it. So see that maybe oh oh I think that this and this are the same. I prepared two different slides, but unfortunately the first one was just deleted, and second one is copied twice. So sorry about that, but let's skip the deleted one, and let me just directly go to this one. And anyway, when we calculate the time derivative at time index t sub k, then if we take this quantity at t sub k, then maybe you have to write down in this way: limit of our delta equal to 0, and we can think the quantity t sub k plus delta minus c tk and divided by delta. That is one form for our time derivative. And you know that in our discretized form, we have no ability to have really infinitesimally small delta value. So what is the minimum value we can assume in this case? This delta is not real space delta, but this is time domain delta. So we can assume that maybe this tk plus 1 minus tk, the difference between two neighboring time instances, is the minimum one we can achieve in this discretized system. So under this assumption, this delta is just used for this one. Then let me just write down. Then what we can do is now tk plus 1 minus tk, and here in upper part we have tk plus 1 minus tk, so here we have tk plus 1 minus tk. Okay, so what is it? This is the form shown here. Okay, so simply speaking, the first form shown in this first equation just says that taking or considering the limiting form of our time derivative and just this infinitesimal delta as the time difference between two neighboring time. Good, looks perfect under the discretized form our time derivative. But please note that also we can try different form like this. Here, when we try to calculate the time derivative at the same time, we can also think about this form. C at t sub k minus C at t k minus delta. So are you with me? So if delta goes to 0, these two types, left limitation or left limit or right limit, should be the same. However, unfortunately our delta cannot be approaching to really small number 0. So we have to consider this one. In this case, let me just say that now this delta is just once again tk minus 1. Then what will happen if we just insert it to delta? Then we immediately have the values or expression shown here. I mean that just taking the definition of our time derivative and applying the limit of our time resolution, then we find two different forms for the time derivative. One is the delta goes to 4 starting from t sub k, and we are consulting on or relying on the values at t sub k plus 1. And in this lower case, starting from t sub k, our present time instance, we are referring the quantities at t sub k minus 1, the past value. So simply speaking, I want to summarize like this. In this Ford-Euler scheme, the time derivative is calculated by taking the difference between future and present values. Here, future means that the values at t sub k plus 1 when tk is the present. And in the case of a backward Euler, on the other hand, the time derivative is calculated by taking the difference between the present and past value. Here, once again, present means the t sub k and past is t sub k minus 1. So, at first glance, maybe you feel, now I'm just talking about seemingly obvious thing many times. However, they are quite much different. Please note that they are different. So, discussion on all kinds of these differences beyond the scope of our lecture. Okay, so then what is our choice? What is our choice in this course? We will always take this backward scheme. Backward scheme means that once again we take the time derivative by using our present value and the past value. So that is our choice. Then backward Euler scheme, then time derivative terms can be represented in this way. Previously we have already discussed about backward Euler scheme, then that's it. But you know, this is this is a time derivative at a certain point, xi. Here xi can be x0, x1 up to xn minus 1. So in the discretized form, actually we have to sample them at these endpoints and make a vector. So simply speaking, we are now working on a solution vector, and the solution vector is just given as C at xo, C at x1, and Z, the last point here. Of course, that is quantity at t equal to tk. So if we wanted to calculate the time derivative of this quantity, the time derivative of this discretized vector, then what we have to do is taking the backward-Euler scheme. Then if you remember, backward-Euler scheme just takes the time difference between present value and past value, present value and past value. Also, we have to consider the solution vector at present time and solution vector and past time. So please note that although everything looks the same, but here we have a different time indexes. Okay, so are you all with me? So I think that's not that difficult. So let me just make a concrete example. For example, when time equals 0 second and when time equals 1 second, a C vector has value of 1, 2. Then at t equal to 1 to t equal 1 second, now we have 10 and 100. Then what is the time derivative of this solution vector? Then we can say that 1 minus 0, this is the time difference, and difference between this solution vector. So we will have 9 and 98. So that will be the time derivative of our solution vector. It looks quite easy, but anyway, point is, in this backward-Euler scheme, this kind of the time derivative of our solution vector is assigned at which time instance? Is it assigned to 0 second, or is it assigned to 1 second, 2 second, or another one like a 0.5 second? So what is the answer? The answer is, if we take the backward-Euler scheme, then we have to assign this quantity at this 1 second time point. So this is really important, where we assign this time difference to which time instances. If I have no previous knowledge on this scheme, then if you ask me the same question to me, I would like answer like this. Maybe this one should be assigned to 0.5 second, because this is the difference between 0 and 1, and it is quite obvious to assign this intermediate quantity to the intermediate point. So we have already applied this kind of philosophy in our previous real space discretization. Do you remember it? So when we calculate something, second order derivative, so since we take the difference between x sub I and xi plus 1, our first derivative was assigned not here, not there. Previously we assigned to the where? To the midpoint. Also, it was assigned midpoint, and their difference was also assigned at the midpoint. So that was the philosophy we have applied in the real space discretization, but especially for our time discretization, we intentionally take this kind of approach. Instead of assigning it to the midpoint, we intentionally assign it to the present point. So it is important. So let me just once again emphasize it. So let's say that your C value at a certain position grows quite rapidly. For example, yes, this is time variable and this is the actual behavior of your C value. Then now let's assume that you have here certain time point and another time point and another time point and another time point. This, let's just assume that this is actually your solution. Then what the backward Euler scheme state is, when you try to calculate the time derivative at this point, round C over round T at this point, the exact solution would be like this. However, what you are doing right now is, instead of taking this real derivative, it is not possible, but you calculate just the slope shown here, and this slope is assigned to the derivative, time derivative of this point. So we assume that, okay, time derivative is just like this. Obviously, even for this simplest example, you can find that there occurs certain discretization error. So since we are taking the derivative between present value and past value, it is not that perfect to consider this kind of behavior. But anyway, please note that although that is not perfect, but this kind of backward schemes are the schemes of our choice. Okay, do you have any question on this backward scheme? So please feel free to ask me any question.
좀
Yeah,
please. 그 백월에 대해서 한 포인트를 해가지고 이제 앞뒤 해가지고 이제 거기서 이제 델타 x로 나왔었잖아요.
Yes.
그러면 한 포인트에 대해서 예를 들어서 이 포인트에 대해서 이 이분값을 구하고 싶으면 이 지점과 이 지점 해가지고 이 델타 x를 해서 나누면.
So let me just repeat his question once again in order to understand. So first of all, let me state your question once again, and if that is my understanding is correct, then let me answer. His question was like this. Let's say that we have a certain C function, and here we are talking about t sub k and tk plus 1 and tk minus 1. In this scheme, backward order scheme, we take the difference between this and that and assign the average slope to here. That was backward order scheme. But his question is, why don't we, instead of taking the difference between this and that, why don't we take the difference between this and that and calculate the average one and assign it to here? If we take in this way, then it's good, because now we take just values at past value and future value and calculate the present value. So there is that it follows the trapezoidal rule perfectly. So of course in this case our delta is not no longer the smallest one, our distance or delta value should be this way, twice longer. Am I correct?
Yeah.
Okay, so how about your opinion? Sounds great, but point is that was really good. I think that was a really good question, but please note that we are doing time march. So your suggested way is quite good when we have past value, present value, future value at the same time. But unfortunately, we are doing so-called time marching approach. So we assume that we know past value. However, we are now trying to calculate present value, and there is no hope to us to calculate the future value right now. So unfortunately in this case, the value at the future time instance is hopelessly unavailable. And in the case of this present one, by solving our equation, we are now currently trying to calculate this value. So although your question was, or your idea was quite brilliant, but unfortunately it is not available. However, I wanted to tell you that your approach itself is actually used in the slightly different context. For example, that was a really good question, so let me just think about this one. The limitation explained by myself was all related with this so-called time matching approach, because we assume past is known and now we are trying to calculate present and future is not known at all. However, we have also different problems. So different problem means that here we have time, and sometimes we have to solve a problem whose solution is periodic with given time period capital T. In this case, our boundary condition, time boundary condition is the initial and the last time we have to have the same quantity. C sub xi equal to 0 should be the same with T sub xi plus capital T. In this case, maybe it would be very difficult for you to calculate this the solution satisfying this periodic boundary condition. So in practice, what we do is now set all of these points, quantities at these time instances as unknown variables at the same time. Then in that case, maybe your suggested approach can be quite useful, because in that case everything is unknown and we are now trying to calculate this one. So let me just come back my slide previously. Oh, so maybe you remember that I have wrote many things here. At the time we have x and t, and time matching shows that we calculated time quantities and time quantities and time quantities. This is time matching. However, if we adopt a way like x and t, if this entire two-dimensional space are discretized and solved at once, in that case you can try to adopt your suggested discretized scheme, like taking future and past at the same time to calculate that present value? That was a really good question. However, since we are talking about time matching, unfortunately, that seemingly more accurate calculation cannot be done. That sounds a little bit disappointing, but please note that all of these time matching quantities or time matching schemes have the common features, like if you take the small time distances, if this one goes to 0, then every scheme give you good enough solution. Okay, so therefore the point is whether which scheme is better or not. It really depends on the opposite case. If we have reasonably crude time mesh or time points, then what will happen? Everything goes to perfect for good situation, under the good situation. However, if we have a bad discretization scheme, then eventually it will fail much earlier when we have large time difference. Okay. Anyway, that was a really good question, and I wanted to encourage everybody to ask me any question, because your question, we have seen right now, his simple question was initiate quite a long discussion about the time matching and other kind of solution method. So you will get more if you ask me more. So anyway, so up to now we have successfully discretized our time derivative. Then now let's try to make the entire diffusion equation. So left hand side was round c over round t, and right hand side was second derivative. So I will just put it here. So now you can read it. What is it? This is nothing but round c over round t evaluated at timestamp t sub k. Of course, this is under the assumption of backward Euler scheme. So we are using the backward Euler scheme. Then this is just the time derivative. Then please try to read this one. Can you read it? So here we have leading coefficient d, so diffusivity, and now we have remaining one. Wow, what is this? This one is simply the discretized form of second derivative of our c. So are you all with me? So now now this is the system, but please note that always when we talk about this numerical simulation, we have to be careful about boundary conditions. So everywhere means that x1 up to xn minus 2. It's easy and straightforward. And how about the boundary? In this boundary, so I assume that x0 at any time instance is equal to x or the same point and the initial value. Also, I assume that the right end also we have the same condition. So at two boundaries we have no change in its value. I mean that, for example, let's think about this one. This is now real space, and initially the dopant was distributed in this way, and now we introduce sufficiently wide simulation domain. So let's say that this is 0 and this is your L value. Then we say that initially the density is 0 and density is 0. Good. Because at the initial case, the dopants were quite localized at the center point. After that, let's assume that you do the thermal diffusion. What will happen to this guy? If you have thermal diffusion, then maybe you will have widened distribution of your dopants. And also what will happen? If time has elapsed or further, then you will have more widely distributed value of your dopant profile. However, until this end touch the right boundary and touch the left boundary, this kind of assumption is quite valid. Are you with me? Of course, let's say that now time has elapsed sufficiently, then now this front, left front almost close to the left hand, and right front is quite close to the x equal to L. In that case, the boundary condition we have assumed up to now is not good enough, because now we have really the non-zero dopant profile, so it is no longer a good approximation or good boundary condition. But please have a look at my suggested form here, and please try to read it. What is it? Here we have all 0 and C vector. So this null row vector gives you just null for the first one. And also the operation of this null vector, null row vector, and this C vector gives once again a scalar 0. So if we read the first law of our discretized diffusion equation, then I would like to say tk minus 1 minus c at tk minus c at tk minus 1 equal to 0. This is right hand side and this is left hand side. Simply speaking, the boundary condition I have applied right now is the difference between concentration at different time points is just 0. Simply speaking, at x0 or at xn-1, the density is just preserved. We have a constant one fixed as the initial value. That is my suggestion. So are you all with me? So now if we have this kind of description, then now we can make the solvable form first. Now we assume that at t quantities at t sub k, the present values are treated as unknown variables. This is present. While the values at t sub k minus 1, that is past, and quantities at this past instance is taken as known values. So our goal is from these known values to calculate these unknown values. So let me just manipulate it. How can you manipulate it? So here, now just to label them. Do you know this guy? No, you have no idea. Do you know this guy? Yes, I know. And how about this? Do you know this guy? No, You have no idea. So if you have unknown quantities, then please put them all in your left hand side and put your known quantities to the right hand side. If you take this kind of manipulation, then you will find that, okay, this is known quantities and these are unknown quantities, and of course having certain scalar value or matrix multiplication. Anyway, now you understand your right hand side is known and your left hand side is unknown. So from the right hand side, now you can calculate your left hand side quantity. Then let's go. It can be written as a form of ax equal to b form once again. So how can you do that? This is your b vector.
디메트릭스 1이 돼야 되는 거 아닌가요? 여기 1 되고 1 되고 이렇게 돼야 되는
No. Please. That is really good question. That is really good question. Intentionally, this first law and the last law has all zero values. Why? If we have this slide here, we have all zero first law and all zero last law to impose our boundary condition. If we have, for example, 1 and 1, then it does not satisfy the boundary condition. Why? If we have this kind of thing, then our boundary or our discretized equation now becomes, okay, that was a really good question. Now, if we have non-zero right hand side for our boundary values, then we have delta t here. So delta t means that the difference this one, and this one is shown here, this one is shown here. And if we don't have non-vanishing quantity, for example like 1, then we will have d over delta x squared times c at given time at t sub k. Then your quantity at t sub k is no longer equal to c at t sub k minus 1. So you have no constant values at these boundaries. However, yeah, so his question really demonstrated the importance of applying the boundary condition. So thank you. I mean that whenever we talk about the discretization of such kind of real space derivative, always it considers certain kind of bulk points. So here bulk points means that the point starting from x1 ending at xn minus 1 n minus 2, sorry, they are not related with the contact points. However, when we consider these boundary points like x sub 0 and xn minus 1, we cannot no longer apply the original form of our equation, because our equation should be augmented with boundary conditions. So they are special. So I want to say that although I have written in this way to simplify our equation, let me just write down more detailed view like n equal to 6 case. Then you will find that actually these two boundaries are really small portion. So 0, 1, 0, 0, 0, 0. Here we have 6 rows and 1, 2, and 6 columns. So this all 0 rows, the first and last, they are assigned for our boundary conditions. But for all others, we have this 1 minus 2, 1, 1 minus 2, 1, eventually 1 minus 2, 1. And all other empty entries are just having 0 in this value. So you know that in the realistic case, we have a very long dimension along this low dimension. So you know these 2 points are just quite part of very small part of our entire equation. So although I write down it is hidden like this. Okay, so now we can come back. Now we can say that this can be regarded as our B vector, known vector B vector, and now this one and this one are the same, and they can be treated as X vector, and this is X vector. They are the same. And finally, we have the multiplication of a scalar value 1 over delta t, and 1 over delta t multiplying just 1 over delta t can be regarded as 1 over delta t multiplying also an identity matrix, an identity matrix whose size is n by 1, n by 1. Because we are working on vector multiplication, so if we multiply this n by 1, oh sorry what happens, and not n by 1, so I mean that identity with n by n matrix, identity matrix. So if we multiply this n by n identity matrix to our x vector, then it just mapped onto x vector once again. So this multiplication of a scalar value can be regarded as just scaled identity matrix. Here we have another matrix and we have the full form. So now we understand our A matrix can be regarded as just identity matrix whose size is n by n and multiplied by 1 over delta and having the second term that is related with time derivative. So when you have a look at the matrix A, you can find two physical effects. What is it? This one is originated from your time derivative, and the second one is originated from your real space derivative. So these two physical mechanisms are combined into our A matrix. So that's the reason why by solving this A matrix we can consider the combined effect of time derivative and real space interaction. So sound quite reasonable. So now we have AX equal to B form. Then by multiplying inverse of A, then now you can calculate X. Then what is the X? X is just the dopant profile at the present time instance. What you do is, once you get the quantities at T sub k, then in the next step, please treat T equal to T sub k as a past time instance. Instead, treat T sub k plus 1 as the new present time instance. By changing the definition of past and present, then now you can merge until you arrive at a given time target value. So simply speaking, This slide just shows that implementation. Once you please start from the initial dopant profile. Who decided the initial dopant profile? Usually ion implantation determines the initial dopant profile. You just introduce a lot of impurities at a given position, well-controlled way. After that, you apply high temperature. So initial dopant profile is usually the initial um, dopant profile just after ion implantation step. So after that, calculate new dopant, so sorry about that, my typo, new dopant profile by solving the discretized diffusion equation and repeat this process until the time reaches at its target value. So what is the target value? Who decides target value? Process engineers gives you the target value. For example, I just apply 60 minutes, 1 hour, or 15 minutes, quarter hour. Then please predict the dopant profile. What will be the junction depth? That is the question. So now let's go to an example. Boron diffusion. Let's say that we have introduced boron whose aerial dose is given by 2 times 10 to the 13 per square centimeter. So simply speaking, if we have this vapor here, this is the top view, we have a very thin vapor, then we just put our impurities into this vapor. Then here 2 times 13 means that if we have 1 centimeter and 1 centimeter, if we have this small square, then we can find 2 times 13 impurity atoms injected from the external world. So this is the aerial dose we want to have, and let's assume that this is just a lateral view, and now make a vertical view. Here we have surface and ions were injected, and let's assume that by some means we have made a very sharply distributed ions at a certain position. Initially, all atoms are just confined or placed at this point. After that, let's assume that we have applied the heat, high temperature, 1100 Celsius for 60 minutes, 1 hour. Then what will happen? Of course, what you expect is, although initially that was highly concentrated, since we have so steep difference, so after time elapsed, maybe it is distributed or distributed or distributed if we increase the process time. That is explained here. In order to solve this problem, we must calculate diffusivity. Previously, we remember that one student asked me this good question: why we don't care about D value when we consider this steady state condition. This is discretized form of our diffusion equation. However, when we consider just a steady state solution, what happens? At the time, we have no terms related with this time derivative. So this one becomes just simply 0, and that's the reason why we were able to kick out this quantity. And previously we just solved only this form, scaled version of our second derivative. However, right now we have the full equation having non-zero time derivative, so we cannot kick out this guy anymore. Therefore, we have to understand what is the value of d. Fortunately, from the experiment, it is known that the diffusivity of our impurities usually follow this form, Arrhenius form. And here we have a coefficient, and this is activation energy. And this is the temperature of our processing. So in this case, we have to use 1100 Celsius, although T is written in the absolute temperature. So now for boron, for this specific species, we have given value already known and given value already known. Then if we calculate 1100 Celsius, then the diffusivity is about this number. Order is given like 10 to the minus 13 square centimeter per second. Maybe in this semester we will also consider so-called device simulation. In the device simulation also we have diffusivity. This diffusivity is the diffusivity of our impurities, and we will consider diffusivity of our electrons inside silicon and diffusivity of holes in the silicon material. Then what is it? It is orders of 10 square centimeter per second. This quantity, not exactly 10, but it's order of 10. So when you have a look at their difference, so since it is motion of our impurity atom, and this is related with motion of our mobile carriers, although they have the same diffusivity, there are quite much difference between its values. Okay, so now let's go to so that's the reason why the required time scale is much different. So although we can operate our device within nanosecond or picosecond, but in this case, in order to move our one atom from here to there, we need the time scale of minute scale or hour scale. So let's go. Of course, you have to implement this one. Therefore, you need some simulation parameters. So this is my suggestion. So please use 10 nanometer as a uniform spacing. So if you have this 1001 mesh point, then you have 10 micrometer long system. And let's assume that your initial dopant is just concentrated at x equal to 5 micrometer. So quite simply here at the 500th point, you have the initial dopant density like 2 times 19 per cubic centimeter. Oh, something wrong. Previously, the problem itself gives you the quantities like 2 times 13 per square centimeter, but I'm saying that different number and different unit. It is intentionally done because since we have 10 nanometer spacing, so when we multiply 2 times 10 to the 19 per cubic centimeter multiplied by 10 nanometer, then this 10 nanometer is corresponding to 10 to the minus 7 centimeter, as you know. So therefore we will have 2 times 10 to the 13 per square centimeter. So this quantity was obtained from the specification of our problem or example. So since we have 10 nanometer, then this delta-like profile can be approximated as 2 times 19 per cubic centimeter. Of course, if we have more bold approach like 1 nanometer, then your initial condition should be 20. Because we are talking about approximate form of a delta function. So delta function simply says that the integration over given range gives you certain given number. So we have to be careful about this one. And all other points, the concentration vanishes. So we have the initial condition. And since our goal was 1 hour or 60 minutes, so time evolves from 0 to 3600 seconds. And what is delta t I have used? So I used 10 seconds as a delta t. Of course, you can try different numbers. One way you do is reduce delta x or increase delta x. Also another one is you can reduce delta t and increase delta t. Of course, the best solution can be obtained when you have smallest delta x and smallest delta t. However, what is the smallest? There is no limit. So therefore, please take the reasonable value. In order to solve this simple problem, let's say that you have spent 1 week or 1 month. Is it reasonable or not? It's not. You don't have to waste your time on this simple problem. So please try to use reasonable values, reasonable simulation parameters to calculate this quantity. So now let's go to the result, simulation result. And starting from time equal to 0, I selectively chosen values at 400 seconds, 1600 seconds, and after 1 hour. This blue one is the quantity after 400 second diffusion process, and after 1600 it is more widely spread, although the peak is reduced. It is quite reasonable because previously it was concentrated on a certain point, but now it is distributed. Therefore, not only this span is expanded, but also this peak should be reduced. Of course, if we integrate this blue curve or this orange curve or green curve, the area underneath the curves should be the same. And you can see that now 400, 1600 and 3600 seconds, now you have reduced. And analytic solution suggests that the peak is reduced in this way, 1 over square root of time. So that's the reason why, if we take this one, this is corresponding to 20, and this is corresponding to 40, and this is 60 when we take square root of t. So we will find that when this is reference and this is just half of it and this is just 1/3 of it, please check my suggestion by using your own simulation result. So let me conclude today's lecture with homework number 4. You have only one problem. Please implement the diffusion solver. So what you have to do is just to implement this AX equal to B system shown here. Yes. Oh, where is it? So yeah. Please construct your A and every time calculate B and taking inverse A multiplied B, you can calculate the C vector. So please calculate the C vectors. For example, 360 times to get the solution at 1 hour later. Okay, so yes, homework is quite simple, and please verify your simulation result with the graph, this graph. Please draw your own graph and compare with, this figure. And also, please test the same problem at lower temperature. Since we have 100 Celsius degree lower temperature, your D is no longer orders of this number. There will be much smaller number, like orders of 10 to the 19 or 15 in this scale. So therefore, if we just take these simulation parameters, time scale and real space, then you will see almost nothing, because diffusion is quite much suppressed. So my suggestion is, please reduce the scale of your real space, because your dopant does not diffuse quite much. So, and please test your program, your code at reduced temperature, and since the temperature is quite low, then diffusion is now suppressed. So please modify your simulation parameters for this lower temperature. That was all for our homework, and quite as usual, your due is next Monday morning. Okay, do you have any question on homework specification or the lecture contents? Any other question? No? Then, okay, thank you for your attention, and to wrap up today's lecture.